Alkyl halides undergo substitution reaction. The basis of the substitution reaction is the nucleophile attacking the electrophile. So you use a full head arrow in order to show the transfer of the electrons from the nucleophile to the electrophile. Now, normally in substitution, the electrophile or the electrophilic carbon has a leaving group next to it. So when the nucleophile attacks the electrophile, the leaving group is going to leave. There are two different mechanisms, and each of these mechanisms, they go by their own rules. S stands for substitution, N stands for nucleophilic, and 2 and 1 stands for the order of the reaction. The general reaction involves a reactant, a reagent, a solvent, and then the reaction conditions, and there if they are present, and then of course the product. What determines the reaction if it goes by SN2 or SN1 is the type of the alkyl leaving group, the type of the nucleophile, and the solvent. So there are three conditions that we would need to go over. The solvent type, because the solvent type is important to determine if the reaction goes by an SN2 or SN1, the type of the nucleophile, and the alkyl leaving group, the type of the alkyl leaving group. So we're going to go over each one alone. For the leaving group, so let's start with the leaving group first, and then we're going to talk about the alkyl leaving group. So for the leaving group, by definition, a good leaving group is a leaving group that is a weak base. To be a weak base, it has to be generated from a strong acid. So for example, we say that iodine, I minus, Br minus, Cl minus, all of those are excellent leaving groups. And the reason why they are excellent leaving groups because they do come from a very strong acids, which are the HI, the HBr, and the HCl. F minus is a bad leaving group because F minus is generated from the weakest acid among all of these acids. Even though HF is still a strong acid, but compared to all of these acids here, the halogen acids, HF is the weakest among all of them. So its conjugate base is supposed to be stronger than any of those conjugate bases. And by definition, a leaving group is a good leaving group if it is a weak base and not a strong base. That is going to make all of these halogens suitable halogens for being a leaving group. Another good leaving group is water. Water is a weak base and it is a conjugate base of H3O+. So all of those are considered to be excellent leaving groups when it comes to nucleophilic substitution. On the other hand, we have conjugate bases that are very strong because they are derived from weaker acids. HF is a weak acid. Water is a weak acid because the pKa is very high. Ammonia is the same thing. Hydrogen is the same thing. So if this is a weak acid, then its conjugate base is going to be a strong base. So that is going to make all of these leaving groups not suitable for substitution reactions. There are two other examples for leaving groups, and these leaving groups, there are excellent leaving groups. These are derived from very strong acids. These are even stronger acids than HI. If you look at the pKa table, the stronger acid that we've been working with so far is HI. This one is stronger than HI. It's called para-toluene sulfonic acid. We went over this one before. So when para-toluene sulfonic acid, which has a pKa of -10, loses its hydrogen, it becomes a conjugate base. That conjugate base is going to be a very weak base. We abbreviate that as OTS, and this is the TS group, which is the tosyl group. This is an excellent leaving group because it is a very weak base. Same thing for the methyl sulfonic acid. This is also a strong acid. If you lose the hydrogen of this acid, then you're going to end up getting your conjugate base. This is the MS part over here. So that is the MS part. So you abbreviate this as OMS, and OMS is a very weak conjugate base, so it's an excellent leaving group. So in this chapter, we will be working with three excellent leaving groups: halogens, OTS, and OMS. And all of those, they will be connected to an sp3 hybrid carbon. So all of those will be connected to an sp3 hybrid carbon, which makes the sigma bond, which makes this sigma bond in each one of those a long and a weak bond. So this is why the sigma bond can be broken easily when the nucleophile attacks any of these R's in there, so that the leaving group can leave. Now, the type of the leaving group, um, it does not affect the reaction whether it's an SN2 or SN1, because SN2 and SN1 always happens with any of those leaving groups. The type of the leaving group is going to affect the speed of the reaction. So let's say, for example, if I start with an ROTS versus an alkyl halide. The OTS is a better leaving group because it's a weaker base than the halogen. So this is why the speed of the reaction involving the ROTS will be faster than the reaction involving the alkyl halide. The type of the alkyl halide, yes, it has now an effect on whether the reaction happens by SN1 or SN2. So the type of the alkyl halide, this one is the one that determines or determine whether the reaction is SN1 or it is SN2. Now, before going over this, we've mentioned that there are different types of alkyl halides or alkyl leaving groups: primary, secondary, and tertiary. And all of those halogens or leaving groups, they have to be attached to an sp3 hybrid carbon for the sigma bond to be broken. So if you have an sp2 hybrid carbon that is linked to your leaving group, the reaction will not happen. The reaction will not happen on the vinylic carbon, but it will happen on the allylic carbon because this is a regular sigma bond attached to the sp3 hybrid carbon. Now, for the conditions of the alkyl halide, whenever you are working with an SN1 reaction, you always prefer to start with a tertiary alkyl halide. Tertiary alkyl halide undergoes SN1 reaction faster than a secondary alkyl halide. If you are working with a primary alkyl halide or a methyl halide, then the reaction will not work with SN1. Now, for SN2 reactions, you prefer to start with a less substituted alkyl halide, meaning that you start with a CH3X, which is a methyl halide. This one reacts faster than a primary alkyl halide. Those two react the best with SN2 reaction. You can have an SN2 reaction with a secondary alkyl halide, but you cannot have a reaction with a tertiary alkyl halide. So SN2 does not work with SN2. So SN2 does not work with a tertiary alkyl halide, and SN1 does not work with a primary alkyl halide or a methyl halide. For the conditions of the nucleophiles, there are two types of nucleophiles: strong nucleophile and a weak nucleophile. Strong nucleophiles, they happen with SN2 reactions. Weak nucleophiles, they work with SN1 reaction. So if you take a strong nucleophile in the reaction, you will have only SN2 mechanism. And if you take a weak nucleophile as a reagent, then only you're going to end up getting the SN1 mechanism. How can you differentiate between strong and weak nucleophiles? A nucleophile has lone pairs. So strong and weak nucleophiles, they do have lone pairs. Both of them. They do have lone pairs. Here I'm not showing the lone pairs, but if you want to go ahead and show the lone pairs, here's what you're going to end up having. So the OH will have lone pairs and the negative charge. The N3 minus has a Lewis structure of two double bonds, two lone pairs for each one of these nitrogens, because I do have a final negative charge here. So this nitrogen is positive, and each of these nitrogens are going to be a negative charge. The cyanide is a C triple bond N, where the N has lone pairs in there, and the carbon has lone pairs as well. The carbon is the negative charge. Let's highlight our nucleophile here. So our nucleophile here is the carbon. The nucleophile here is one of the negative charged nitrogens. The nucleophile here is the oxygen. So the nucleophile, by definition, whether it's strong or weak, it should have lone pairs. Same thing for the Cl negative. So this is going to be my lone pairs. Please show all the lone pairs whenever you're working with these reactions. I know that sulfur has 3 lone pairs in order to have a negative charge. The alkoxide, the OR, this one has lone pairs on the oxygen. So it's the oxygen that is the nucleophile. Okay, and then the triple bond has lone pairs on the carbon, so that the carbon is octet. So it is the carbon that is the nucleophile. Then you have your bromine in there, and then the alkyl sulfide. So then the RS negative. So it's the S over here that has lone pairs, so this is the nucleophile. Also, you have the iodine. The iodine has lone pairs with a negative charge, so this one is a nucleophile. I'm running out of room on this one, but this is a CH3. It's a carbon double bond O and an O negative. And the O here has 3 lone pairs. So it's the O negative in here that is my nucleophile. So you write your Lewis structure and you search for the element in the Lewis structure that has lone pairs, and this is going to be your nucleophile. So strong nucleophiles are nucleophiles. Notice for all of them, they share one thing, that the nucleophile has a negative charge. So negative charges are strong nucleophiles because both nucleophiles, strong and weak, they have lone pairs. For example, water has a lone pair on the oxygen, but the oxygen has only lone pairs. It's a neutral. It is not a negative charge. So this is why I'm going to highlight the oxygen. This is the nucleophilic site, and I'm going to call this a weak nucleophile because it does not have a charge on the nucleophilic site. Same thing for ammonia. This is why the Lewis structure is very important. So you have your hydrogens in there, and you have your lone pair on the nitrogen. And again, the nitrogen is a neutral, so this is why it is a weak nucleophile. Same thing for hydrogen sulfide. So you have your sulfur, your hydrogen, 0 charge on the sulfur. So this is your nucleophile and it is a neutral. Same thing for the alcohol. The amine, this is a primary amine. When you identify your functional groups, please identify the type of the functional group that you are working with as well. And this one is similar to water, but instead of one of the hydrogens, I am replacing the hydrogen with the R. So all of those, they share one thing, which is the lone pairs on the electronegative element. So they don't have a charge. Because they don't have a charge, I'm going to call those neutral nucleophiles. So what's the difference between a nucleophile and a base? Because both have lone pairs in there. So by definition, a nucleophile is a base. All the nucleophiles are bases. Let's have an example. OH minus. This one is a base because it's a negative charge. It's a nucleophile because it has a lone pair. So OH minus is both a base and a nucleophile. If it want to act as a base, then it needs to take a hydrogen. And here in this case, it's not taking a hydrogen. It is attacking the electrophilic carbon. So when you have a nucleophile attacking the electrophilic carbon and not taking a hydrogen, then it's going to behave as a nucleophile. On the other hand, if you have your nucleophile taking the hydrogen from the acid, then in this case, the nucleophile is going to act as a base. So there is a difference in the type of the reaction whenever you are working with the nucleophiles and bases. By definition, nucleophiles, they attack the partial positive carbon, and bases, they always take the acidic hydrogen. And keep in mind, it's still a nucleophile electrophile reaction because the base is a nucleophile again, and that is reacting with the electrophile in order to get to the product. When bases are small in size, they can have a double role. They can act as a base or they can act as a nucleophile. However, as the base becomes bulkier in size, it will stop acting as a nucleophile and it will act only as a base. The reason why? Because if you're working with a bulky base, it's easier for that bulky base to come and take that small atom, which is the hydrogen, rather than a bulky base attacking the carbon. There will be no room for the bulky base to fit and do a substitution reaction, but there will be a room for that bulky base to come and grab the small hydrogen atom. So all nucleophiles are bases, but bulky bases, we cannot consider those as a nucleophiles. So whenever you're working with bulky bases, then you will not have a substitution reaction. There is no way for a bulky base to act as a nucleophile. Bulky bases are just bases, and the role is only one thing, to take the acidic hydrogen. An example of the bulky base is a tertiary butoxide. Now, the tertiary butoxide here is coupled with either potassium or sodium. So when you name the base, you name it as the metal first, and then you name the negative charge part. This is sodium tertiary butoxide or potassium tertiary butoxide. This guy is still a strong base. It's a very strong base because it does have a negative charge, and it's a base because it does have lone pairs. But it is not a nucleophile because of its bulkiness. Nucleophiles, they need to be small. Like, for example, this one. This one is a base because it has a negative charge, and it is a nucleophile at the same time because it is small. However, this one is bulky, and the role for the nucleophile is always to attack the carbon, the partial positive carbon. So you need your nucleophile to be small in size to undergo substitution reaction. It cannot be bulky. If it is bulky, then it will act as a base. And as we said, bases only take acidic hydrogens. Another example of a bulky base besides potassium tertiary butoxide that we will work with throughout this course is lithium diisopropylamide. We abbreviate it as LDA. LDA is just a base, and bases take acidic hydrogens. There are two types of solvents involved. The first type of solvent is a polar protic solvent. This type of solvent has OH or NH in it. And these are examples of polar protic solvents. You just need to look at the molecular formula. If you see an OH in there or an NH in any of those, then these are considered to be a polar protic solvent. Like for example, tertiary butyl alcohol. This is a solvent. Acetic acid. This is a polar protic solvent. All of these solvents, they are specifically in order to work with SN1 reactions and not SN2 reactions. If you want to use those solvents with SN2 reactions, they are going to slow down the SN2 reaction. The SN2 reaction will still work, but it will be slowed down. If you want the reaction to work and be a fast reaction, then you would need to use those with an SN1 reaction and not an SN2 reaction. Polar protic solvents, they solvate both cations and anions. When we explain further SN1 reactions, with SN1 reactions, we have intermediates. And the intermediates in the reactions that are forming are called carbocations. So these are cations in there. The polar protic solvents are especially important for cations because what they do is that they wrap themselves around the cation and stabilize the cation. So this is why it's very important whenever you are working with SN1 reaction to use a polar protic solvent. On the other hand, polar aprotic solvents, they work with SN2 reactions only, and those they have no OHs and no NHs in them. Whenever you're working with an SN2 reaction, SN2 reactions involves the use of strong nucleophiles. So here you are using a strong nucleophile. When you add a solvent to the nucleophile, you want the solvent to keep the strength of the nucleophile in the SN2 reaction. So you don't want the solvent to solvate the nucleophile. This is why you want to use a solvent that has no interaction with the nucleophile. The best solvent are these solvents that have no OHs or NHs in there. So there will be no hydrogen bonding. There will be no type of interaction in there. So this is why polar aprotic solvents, these are excellent solvents for SN2 reaction. The examples for polar aprotic solvents are either acetone, acetonitrile. You are responsible to know all of these structures because they will be appearing in the reaction. So you would need to know that these are solvents and you would need to know the type of the solvent. They don't have any NHs or OHs in them. You have the tetrahydrofuran, the DMSO, and the DMF. In most of the cases, we use the abbreviation for the DMSO and the DMF to represent those solvents in SN2 reactions.